Hello everyone, my name is Maybelin Carolina García Chiquito from the Faculty of Civil Engineer at the Universidad Michoacana San Nicolás de Hidalgo. Today I will present our research entitled Intelligent Damage Detection in Historic Searches based on Machine Learning and Multiscale Datasets. This work focuses on the automatic detection of cracks in heritage buildings using deep learning techniques and images acquired from different platforms. Motivation. The inspection of heritage buildings is still performed mainly through visual survey carried by specialists. However, this process is time-consuming, subjective, and particularly difficult when evaluating large monuments such as churches, where many structural elements are located at considerable heights. For this reason, automatic cracks detection based on artificial intelligence represents a promising alternative to support structural inspection, reduce subjectivity, and improve long-term monitoring of cultural heritage. In this study, we select the Santa Rosa de Lima Church, located in the historic center of Morelia, Mexico, as our case study. The methodology. The first stage of this research consists of building a multiscale image dataset. Images were collected using two complementary acquisition methods. First, ground-based photographs were captured using a Sony a7 III camera equipment with a 60-35mm lens. Second, aerial images were acquired using a DJI Mavic 3 Pro unmanned aerial vehicle. The UAV followed serpentine flight paths to document a vault, while circular trajectory were used to capture the bell towers from top to the bottom. This acquisition strategy allowed us to document architectural elements located at different heights and scales. In total, 900 images were collected. Next, all images were imported into RoboFlow. The pre-processing stage includes automatic image orientation, metadata removal, and resize to 60x800 by 60x800 pixels. After pre-processing, every piece of cracks was manually annotated using bounding boxes and assigned to single object class named crack. This annotation process generates a standardized dataset fully compatible with YOLO object detection models. YOLO 11 training. The annotated dataset was then used to train a YOLO 11 object detection model. The dataset was randomly divided into 70-50% for training, 50% for validation, and 10% for testing. All images were resized to 6400 by 6400 pixels, and the model was trained for 150 epochs using a single detection class corresponding to cracks. During training, three loss functions were monitored: boss loss, classification loss, and distribution focal loss. Model performance was evaluated after every epoch using four metrics: precision, recall, MAP at 50, and MAP at 5295. Results and discussion. The training curves indicate that the YOLO 11 model converts successfully during the optimization process. All three training losses continuously decreased throughout the 150 epochs, indicating that the model progressively improved both object localization and crack classification. The validation losses followed a similar trend during approximately the first 100 epochs. After that point, a slight increase can be observed, suggesting the beginning of moderate overfitting while maintaining acceptable generalizations. Regarding the detection performance, the final metrics were precision of approximately 0.26, recall of 0.24, MIP at 50 of 0.70, and MIP at 95 of 0.065. Although these values are relatively low, these should be interpreted considering the complexity of the dataset. Unlike many crack detection studies that rely only on terrestrial photographs or dataset combining ground-based and UAV image, introducing significant variability in scale, viewpoint, illumination, and crack appearance. This heterogeneous image distribution increases the difficulty of the detection task and represents one of the principal challenges identified in this work. Finally, the qualitative detection examples demonstrate that the model is capable of identifying several crack regions, although false negatives and localization inaccuracies are still present. In conclusion, this work demonstrates the feasibility of using YOLO 11 for automatic cracks detection in historic searches using a multi-scale image dataset. The model achieved this stable coverage throughout training. However, detection performance remains limited due to the high variability introduced by combining terrestrial and UAV imagery. Future work will focus on increasing the dataset size, improving annotation quality using higher image resolution, and exploring advanced strategies to improve generalization across different acquisition conditions. Thank you very much for your attention.